All right, let's take a look now at our last two examples. This one involves another musical instrument, a piano. This time we're given the tension, 600 newtons. We're given the length of the wire and its mass. And we're basically asked what sound does it make? What's its fundamental frequency? So a lot of times this is what we're interested in finding anyways, that fundamental. So this is going to be F1. So the first harmonic, N is going to be 1 over 2L, times the speed of the wave in the string, which is the square root of the tension divided by the mass per length. So this is right off my equation card. I've just put the 1 in for my fundamental. Okay, so let's look at the numbers that we have here. 1 over, we know the length, so 2 times 0.4 meters. And the square root, our tension is 600 newtons. We have our mass per length. Then we got to be careful with the mass here. The mass is given in grams. We'll divide that by 1,000. 0.005 kilograms. Never forget to change your masses to kilograms. 0.005 kilograms per, and yet I'm in length here, per 0.4 meters. Mass per length. So in the previous problem we were given that as one quantity. Here we got to find it. We got all these numbers. We can plug them into our calculator. We can figure out what sound we're going to hear. So the fundamental frequency is 274 hertz, and I'm not sure what note that is. That might be like a D or something close to it. So I think it's a little bit above C, which is 250 something. Okay. So the second part of this problem asked me what number of the highest harmonic that can be heard by a person who is capable of hearing frequencies up to 10,000 hertz. So what's the highest harmonic on? So it's the same problem about the same piano string. So this is the fundamental, but there are higher notes that can be played as well. So since I know the fundamental, I'm going to use that to help me do the second part. Say the frequency of the nth harmonic is equal to N times F1. And I know that this person can hear up to 10,000 hertz, so that means I'm going to make the nth harmonic be 10,000 hertz. And that's going to be equal to N times 274 hertz. So how many multiples of 274 can I do? And if I solve this algebraically, I get 36.51. The 0.51 is nonsense. You can't have a pace of an integer. These go in integer number because of the half wavelengths. So must be integers. So that means that I could hear the 36th. Somewhere above the 36th is how high we could go. I couldn't hear the 37th. I can't get up that high, but the 36th is going to be the highest one that we can hear. So that's going to be the answer to this question, the 36th harmonic. So you might imagine you can have a really complex sound to an instrument if they got all 36 of these harmonics, these different musical notes that sound good together, and they're all kind of playing and interplaying amongst each other, along with the fundamental, can give that instrument some real color to it. Okay. Final example, our last one here, we've got a guitar string. We're given its density, again, grams per meter. Be careful with our units. We're given the tension and the distance between them. And this time, rather than a fundamental, we're told that it's oscillating in the third harmonic. And we're asked to find some things about this. So I'm going to begin by drawing a picture of that third harmonic. You don't have to memorize these. You should be able to come up with these just by thinking about our pattern. So the fundamental, the simplest one, is just going to be one lump going up and down. So the second harmonic is going to be two lumps going up and down, and the third is going to be three. So that means I'm going to need three antinodes with some nodes in between them. And you should be able to come up with something like this on your own. A pattern that looks something like this. So here's my third harmonic. And we're given a distance here, the 90 centimeters, which would be 0.9 meters. That's how long the string is from one end to the next as it vibrates. Okay. All right, so there's my picture. We're given some other quantities here. Let's see what we're solving for. First of all, we need to find the speed. So this is a wave in a string, so this is old hat. We've done this before. Square root of the tension divided by the mass per length. And those quantities are all given here. So we'll find our speed. Square root, the tension is 150 newtons. The mass per length is given to me as one number here, 0.72 grams per meter, but I need it in kilograms. I got to divide by 1,000. It's 0.0072 kilograms per meter. So I can plug this into my calculator now and I can figure out the speed. So in this particular string, the speed ends up being 144 meters per second. That's pretty fast. I mean, your eye's not going to be able to follow that. That's, it's about 300 miles per hour, somewhere thereabouts. Then we're asked to find the wavelength of this string. And we look at this. This is all about figuring out the pattern, how much of a wave we're looking at. We need to get good at doing this and finding that we got a crest and a trough. There's one wave and then another one. So we've got a whole wave and then half of a wave. So the length of the wave in the picture is a wave and a half, or 3/2 of lambda. So actually, if you want to add this to your card, this could be a nice thing to put on there. N over 2 lambda. This is the relationship between length and which harmonic we're looking at. In this case, we have n equals 3. We can plug the values in. We have 0.9 meters equals 3 over 2 lambda. We can solve for lambda. So basically, we multiply both sides of this by 2/3. And this particular wavelength is 0.6 meters long for one whole wave. Right, that makes sense, right? A wave and a half, or 0.9 meters. So just, one wave, which is from here to here, is 0.6 meters. And then the last piece, I need to find the frequency of the wave. And I don't necessarily have to use my harmonic equation to do this. Now I've got a lambda and I've got a speed, so probably the fastest way to do that is to use the relationship between speed, frequency, and wavelength. So we'll use the 144 equals frequency times 0.6 meters. Divide both sides by 0.6, and this particular guitar string is vibrating in its third harmonic with a frequency of 240 hertz. Okay, so hopefully that's helpful. You see some examples for how this works out. You get a chance to try this yourself in the homework.